Welcome to the solution video to my own puzzle, Krop Kages. It's supposed to be a solution video, but it's also a test solve, basically, because I intend to upload this to Logic Masters Germany, or, well, better, and the Discord archive today. But I haven't touched this puzzle in 3 weeks when I created it, because I've created it back then and gotten some nice feedback from the people on the Discord server, but I didn't really have the time to upload it. And before I do that, I just wanted to give it another test solve, and I'll just try to record myself and use this as a show-off of the intended solution path. So maybe people who have solved this puzzle can find this video in the hidden comments and just watch what this intended solution path was, and they can compare how well they did. Maybe they found the exact path or found a slightly different one. I have received feedback, as I said, and some people did find the intended solution path exactly, and some took slight detours, but I think it's still fairly narrow, and it's not too trivial. This is also the reason why this video will probably not be very short. As I said, haven't touched this in a while, so I'm probably not too fast in solving it myself. I've forgotten quite a bit of the details, but obviously I know the intended tricky parts. I'm just going to go over the rules real quick. Standard Sudoku rules, standard killer rules, but we have, I'll show the picture, but we have no cage totals. However, we have a restriction on the cage totals in that we have a Kropke rule that is not between individual cells but between cage totals, and we get the negative constraint as well. So we know that basically, for example, this cage and this cage could never have totals that are consecutive or in a 1-to-2 relationship. For everyone who doesn't know, yeah, I mean, I guess I don't need to explain it because it's intended for people who solved the puzzle already, but black dots tell that the cage totals are in a 1-to-2 relationship, and white dots mean that the cage totals are consecutive. So what is this puzzle about? The idea behind it all is basically something I have found tricky to implement in normal Kropke Sudoku, so that's the reason I went for the cage Kropke variant, and it's that I wanted to work with divisibility, and you often run into the problems that when you make long chains of Kropke dots in normal Kropke Sudoku, then the solution is very trivial, and you don't get this in here. So that's basically what I have based this puzzle around. And obviously, one thing we can see from the get-go is that we have this cross in the middle that is all connected by consecutive white dots, and I'm going to color this green. And we can also see that there are no dots between this cross and any other cage. So we divide the grid in 4 regions from the beginning, and we have 2 4x4 regions without any hints, without any Kropke dots, and this is obviously not the place to start. I didn't want to make a crazy negative constraint logic apply in the break-in, so obviously we need to start in these other 4x4 squares. Before we do that, we can use a little logic on this cross first, because there's one digit that can be found out relatively easily, and that's the center digit. because we have consecutive cage totals, and so we are just gonna see what the highest total would be that we can put in this whole string of cells. Let's just work with the horizontal cells, row 5. The highest we could put in the single cell in the middle would be a 9, and then we could go up by 1 because of the Krop dot, so we would have 10 and 11, 10 and 11 on either side. So we would be at 21, 30, and then 51. So we would be at 51 at the highest. We have some degrees of freedom there. So let's try putting 8 in here. When we put an 8 in here, we could go 9 and 10. So we have 19, and another 19 would be 38, and 8 would be 46. So we could still go beyond 46, for 45, I should say. We can go higher than 45, but the important thing to note about is that we will never get to 45 putting an 8 in the center because of the parity of the sum of these 9 cells, because if the center cell is an even digit, then obviously these two cells sum to an odd number because they have to sum to either 7 or 9, and these two cells also sum to an odd number, 7 or 9, so they sum to an even number in total. So we can have even sum of these 4 cells, an even cell in the middle, and this is also going to be an even sum and an even sum over here. So we always end up with an even total of these 9 cells if the center cell is even. That means that we can never put the 8 in here, and we will never get to 45 with the 8. Placing the 7 in here obviously is not high enough, because the highest we can then make the other cages would be 8, 9, 8 and 9, and then we can only get to 41, I believe. So we won't get to 45 like this. So basically we just found out that this has to be a 9, and then the outer cages have to be 8 and 10 next to the 9, and then 7, 9 or 11 on the outside. So this is just an easy grab at the beginning, but it's not gonna yield any more progress in this puzzle. So now we need to look at the main break-in, which will use these 4x4 squares. And as I said, I wanted to implement logic that uses divisibility, and you can see right from the start that each 4x4 block is consists of boxes that are connected in one piece. So you can connect all of these cages following the Krop dots, which means that we have knowledge over the divisibility of these 4x4 squares without knowing what the actual cage sums are. So I'm just gonna start with the top left one because it's, I think, the easier one to explain this, and that is that we have a 4-cell cage here and some 2-cell cages around it, all separated with a black dot. And this is kind of like the first thing to notice about this top left square, because obviously looking at these blank squares, we don't know the exact relationship between two cages. We know maybe there's a 2x1 relationship because of the black dot, but we don't know which cage is bigger. But in this case, we do know which cage is bigger, because the lowest we can make this 4 4-cell cage would be 10 with 1, 2, 3, 4, and the highest we could make a 2-cell cage is 17 with 9 and 8. So we can never make a 2-cell cage twice as big as the 4-cell cage. So what we can take away from this right at the start is that this cell, this box, this 4-cell box, is twice, or rather the sum of these 4 digits is twice the sum of these 3 dominoes. And this also gives information about this relationship, because maybe this here, this cell could be twice the sum of these 2 digits. But as we've established already, this is 10 at the lowest. So even if this 4-cell cage was 10, then the lowest this could be would be a 5, and we can never put a 10 in here. So this can never be twice the sum of these 2 digits. So basically we know that if we halve this sum, we get to this sum, and if we halve it again, we get there. So we have the knowledge that, or I have to start on a different way, because we need these 2 cells before applying the logic. Let's take this cell as our starting point, and we have 2 consecutive dots next to it, and these are single digits, so we can never make them the same, which means that we can never go +1 and +1 in both directions. We have to go +1 and -1. So this is normal Krop key logic for once, but it tells us that these 2 cells, they add to twice the value of the cell in the middle, because basically we have -1 and +1 which cancel out. The sum of these 3 will always be divisible by 3, because it's 3 times the cell in the middle. Now, realizing this, we see that these, let's assume the center cell is called, or has the value x, that we have 3x in here, we have 2x because it's twice the center cell in here, and we have 4x in here, another 2x, another 2x, and then we either have 4x here or x itself. So basically we need to find out if this 3-cell cage could be half of whatever is in here, but that's actually where the negative constraint helps us out, because obviously if this was 1x, so if it was the same as this cell, we would need the consecutive dots between these 2 cells and these 2 cells. So it has to be 4x, and just like that we deduced a relationship among all these cage totals that helps us immensely, because we get 4x and 4x and 2x, which would be 10, and then we have another 2x, 2x, and 3x, which is 7. So 17 x is the total value of these 16 cells. That does appear to be of not much use, but it is telling us that the value of these 16 cells can only take some specific values which are divisible by 17, and we will get back to that later when we want to find out which digit exactly is in the middle, and give us the total of all the cages. Because we want to apply the same logic to the bottom right 4x4, where it's a little more complicated, but actually I think it's easier to find one solution, but it's harder to rule out everything else, because what we can see here is that we again have 2 single cell cages which are separated from the center cage by a white dot, so we get the same restriction as in here, which means these 4 cells have to be divisible by 3. So we get whatever sum is in here, and we go +1 on either side and -1 on the other, and then we get sum of these 4 cells, which is divisible by 3. Now we can see that from each of these 3 cages we have a black dot somewhere else. So black dot to these cages, which are then connected via 2 white dots and another cage between them. So I mean, it's kind of obvious what the goal is in here, that basically this cage is twice the value of this one, and then you have to go down by 2 or up by 2 to get the next cage, which is twice the value of this cell, and just the same on the other side. This is kind of hard to explain, especially for me as a non-native English speaker, but it could theoretically be the case that these cells down here are, or some of them are, twice the value of the cells up here. But obviously, if we were to calculate the values of the cells, then we would end up with non-standard numbers. We would have, like, I believe 1/3 or 1/6 of as a value of some of these cells. So we can find out that it doesn't work, and it actually is the case that these black dots relationships are 2 to 1 basically. So I'm gonna use coloring for that to we lost one to make it clear. So basically the blue cages are always twice the value of the pink cages, and yeah, you cannot make it work if you turn the black dot relationship around. But this black dot relationship, so to speak, is relevant for yeah, finding out the divisibility of the whole 4x4 area, and that is that we established already that these 3 cages are divisible by 3, which means they are 3 times the value of the center cage. So we've got 3, let's call it y this time, 3y, and we can double this cage to get to 2y in this blue cage. Now we are yeah, having the same problem where basically we could walk in the same direction either side, but we could go -1 up here and -1 here, but that would never work because we have to get to different blue cells, blue cages at the end, because obviously this is 2 times this cage, this is 2 times this cage, and these 2 values are different. So basically we always know that we walk +1 and +2 in one direction and -1 and -2 in the other direction. So basically another way of explaining the values of these cells would be 2y in the center, and then we have 2y +1, 2y -1 in these cells, which add to 4y again, and then we have these cages, which are 2y +2 and 2y -2, which we can add up to get another 4y in total. So maybe this is a little complicated and to keep in your head, so feel free to write it down if you want to really follow the logic here. But basically the result of this is that the sum of these cells is 5 times the sum of the cell right here, which was 2y. So we have 10y up here, and we have 3y down here, so we get divisibility by 13 in the bottom right 4x4. And that was basically, I'm already 18 minutes in and haven't done anything really, but this is the way to get into this puzzle, because realizing these two 4x4 squares are divisible by these numbers helps in finding the exact value, because what is used in here is that let's assume the top right is yellow, then we want to work with, I'm taking out the other colors for now, oh, it doesn't work. What we want to work out is that this blue shape down here and this pink shape up here sum to the exact same number, or they rather have consist of the exact same digits, because obviously we can look at the last 4 columns of this Sudoku and we get 4 times 1 to 9, and we can look at the first 4 rows of this Sudoku and we got 4 times the digits 1 to 9, and if we take out these, then obviously we should be left with the exact same in the purple and in the blue. But right here we have to use the relationship between these 2 strings of 4 cells, which I guess I'm gonna color a little bit different again. So let's make it light blue and light pink. We need to use the information which we can derive from having a 9 in here, which tells us that these 2 Kages right here can differ by either 0 or 2, because we can walk in the same direction, then it's the difference is 0, or we can walk in different directions, +1 and -1, and we get a difference of 2. And if we walk in different directions and have +1 and -1, we can then walk another step in the same direction for a total of +9 +2. We also already know it's a 9, so we can use 11 as a value for here maybe, and 9, 8, 7 as a value from here. So the maximum of a difference I could make between the light pink 4 cells and the light blue 4 cells would be 21, which is 10 plus 11, minus 7 plus 8, which is 15, so the difference would be 6. These 2 strings of 4 cells have a maximum difference of 6, is basically what we learned from the logic on the cross. So we also know that pink and blue, or rather dark pink and dark blue, have a difference of 6 at the most. So we can now go through the series of numbers that are divisible by 17 and by 13 and find out that there's only one solution to this whole problem. So we know what we need to look at first is what would be the minimum value of these 4 or these 4 cells, and what would be the maximum value, because we need to find a window in which we compare the 2. And the lowest this could be is obviously 45 in the cage, and then we have 1, 2, 3, 4, 3, 2, 1. So that's basically the lowest we could go in here, which would be 10, and then 1, 2, 3, so 16 and 45, which is 61 in total. And the highest we could have in these digits would be 9, 8, 7, 6, 7, 8, 9, with 45 down here. So we would have 30 and 24, which is 54, and then 45 in the box, and we would end at 99. So basically, in every Sudoku that's the case, these 4 cells have at least a value of 61 and at most a value of 99. So we are going to use that and look at what's the lowest, or what are the possible digits in between that are divisible by 17. And these would be 68, I believe, and 85. So that would be the possible values for up here. 85 plus 17 is higher than 99, so we don't get another possible value. And down here we need to look at digits divisible by 13, and that's a little more complicated now. 39, 52, 65 would be the lowest, I believe, and then 78 and 91, and that would be it. So we got these numbers, and we realized that the only 2 numbers we can use that have a difference of lower than 6 are 58 up here and 91 down here. So basically this is the break into this puzzle, because now we know the exact sums of these 4x4 squares, and we can deduce the base cell of each of these squares, which would be 85 up here divided by 17 is 5. And down here we had 91 divided by 13, which would be 7. So we have a 7 in here, which I can't really put in, except for putting 6 and an 8 on either side. So we have a 6-8 pair here, and this is a 4-6 pair here. So yeah, that's basically all the thinking that we needed to do before actually starting in this puzzle. And right now we have found out the values of all the cages in these 4x4 areas, so we can start working on them a little more. Basically right here we have the value of 7, which could never be 6 and 1 because we have the 6 already used up, so we only have 2, 5 and 3, 4 available. And then we can see immediately that this has to be the 14 cage because it's twice 7, and the 14 cage cannot be 6-8 because we have 6-8 already used up. So without 6-8 there's only one solution to this, which is 5 and 9. But this takes away the 5 from this cage, so we are left with 3 and 4 for the 7, and can continue on the logic around here. This should now be either a 12 or a 16 cage, same as this. But we also know that in this 45 cage we have 3 pairs already, so basically these cells are 1, 2 and 7. Now let's see, this right here was a 14 cage, so the lowest this could be is a 13 cage, and in the 13 cage we could never have a 1 or a 2. So this cannot be a 1 or a 2, it's a 7, and we actually get another pair and the third digit in this puzzle, which is a 7. And now we know that we have 3 as a sum in here, and we have a total of this cage of either 12 or 16, but we see we can never get to 16. We can only get to 12, and only by putting a 9 up here, which makes this whole cage 12 sum, and this a 6, this an 8, and this is 16, which 16 in 2 cells can only consist of a 9 and a 7. We have also now deduced that when this is a 12 and this is a 14 cage, this has to add up to 13, and 13 minus 7 is 6, so we get a 6 in this cage, and we know that this cage right here sums to 15, but we have not too much information about what digits could be inside. Now, top left is a little more tricky. We know that we have a 10 cage here, 10 cage here, and a 10 cage here, and then two 20 cages, but I'm not too sure if we can find out too much about these before looking at the central cross again, because what we also realized in the break-in, but we did not put in the cages yet, is that we have a total value of 85 in the top left and a total value of 91 in the bottom right, so we have a difference of exactly 6, and we need to level this difference by making this string of 4 cells exactly 6 higher than these four cells to not break the top right 4x4. So we know that this has to be 6 higher than this, and there's only one way of doing that, and that is by making this a 10 cage as well, this an 11 cage, and this right here would be 8 and 7. So it's a little tricky to denote that, but I'm going to use corner pencil marks for this, even though I'm going to have to delete them later to not confuse myself. But 7 cage is actually quite interesting because we have 2 6s pointing at the 7 cage, so we know this cannot be a 6-1 cage, and we have a 3-4 pair pointing at it, meaning it can never be a 3-4 pair. So actually the only values for these cells are a 2-5 pair, which we can already disambiguate because of the 1-2 pair down here. So we get a 5 and a 2 in the 7 cage right here. Now the 8 cage should consist of not 5-3 because we have the 5 used up, not 2-6, so there's only 1 7 left. We have a pointing 7-9 pair here, so we get 1 and 7 in here. Let's see, we also know that the same logic that applied to the top right obviously needs to apply to the bottom left as well. So these 4 digits have to be 6 higher than these, and that's the same relationship as up here. So we get a 10 and 11 cage here, and right here I'm gonna denote it the same way. No, that's wrong. This way, with the 8 cage and the 7 cage. Now we can do some pencil marking in these 4 cells, which should be 1, 3, 4, and 8, and we can take out the 8 from here and the 3, 4 from here, and the 1 from here actually. So that's basically the main break-in, and as far as I remember, so from here on out I'm gonna have to keep looking for the next deduction myself, and it's gonna be quite the complicated puzzle for me as well. But let's see where we go next. We know these 4 digits, they should be 3, 4, 6, and 8, and we also know that we have to get to 10 and 11 somehow. The only way of making 10 with these digits is 4 and 6, so we are left with 8 and 3. which gives us a 4 and 6 pair in here, and basically yeah, restricts this box a little bit, because we cannot make this 4-6 now. We could still make it, let's put in the numbers 8 and 2. We can kind of put it the other way around because of the 8-3 down here. The same goes for 3 and 7, and obviously we could make it 9 and 1 in either direction. Now let's have another look. Five, 10, 20. So yeah, let's use this next bit of logic here. Looking at column 5, we have an 11 sum, a 10, an 8, and a 7. So we realize quickly that we can never put the 1 up here, because it would need a 9 in this cage, which it cannot have. And then the 1 couldn't be here, so the 1 is actually somewhere down here. So yes, I'm gonna delete the 7 and the 8 pencil marks now and put in normal 1 pencil marks down here. And then we realize that we have a 1 and the 1 in here, putting a 1 in these 3 digits, these 3 cells, and we have a 9 here and here, putting a 9 in the same 3 cells. And we realize that this has to be a 10 cage, so it can never have a 1 or a 9, because it would need another 1 or a 9 down here, and that doesn't work. So taking out these two, we actually get a 1-9 pair up here, which add to 10, so this domino also has to add up to 10. Now we realize that these are both dominoes that add to 10, these can never be 4 and 6, so and these can never be 1 and 9 as well, so basically these can be 2, 3, 7, and 8 only. And the same applies for this one. If this was a 1-9 pair, it would look at this and it would break. So this is a 2, 3, 7, 8 pair as well, and now we get a quadruple, ruling out the 3 and the 8 down here, which now is a 1-9. And we get that this has to be a 1-9 and the 4-6, so one of each pair. But looking at the total sum of this cage, which is 20, we know that we cannot put a 1 in the 3-cell 20 cage, because we would need 19 in the other, so this cannot be a 1. The 1 definitely has to be in here, and it needs a 9 to go with it. And now we also know that the 9 is definitely in here, and it needs another 11 to get to 20, and we have either a 4, so we would need a 7 down here, or we have a 6, so we would need a 5 down here. These are the only two values for this cell down here. Now I'm gonna take a look at column 8, where I know we have quite a restriction going on, because we basically know 5 digits down here, 3, 4, 2, 6, and 7. So we still need 1, 5, 8, and 9. So we can put 1, 5, 8, and 9 in these cells up here. We cannot put a 1 or a 5 in here because of these two. So we're left with 8 and 9, and up here we are still not too knowledgeable, but we will get there. Basically, we need to take another look at this cell, I think, which cannot be 1 and, I mean, it needs to add to 10, it cannot be 1 and 9, it cannot be 4 and 6, so it actually is 2, 8, or 3, 7. Let me think about this for a second. So maybe we might have to pencil mark a little before I remember the next step. We definitely know that this has to sum to 10 as well, and it cannot be a 1, 9. So let's use pencil marks 2, 8, 3, 7, or 4, 6. And maybe I can already remove one of those, but I can't see it right now because these two cells are the same, so they don't see anything here. Yeah, not quite. But this one has to be 11, can't be 9 and 2, so it has to be 3, 8, 4, 7, or 5, 6. But what we do know, and what we have realized in this, is that the 8 has to be in one of these 4 cells. That's basically the result of having an 8 cage and a 7 cage down here, where we can put the 8 in. So the 8 is in these 4 cells, and this has some effect on this cage because obviously we need to pencil mark these two 8s right here, taking out the 8 from here and here. But now we definitely know the 8 is in these 3 cells, it can never be here, so we can take out the 2 from these, and we get a 3-7 pair here finally. So we know the 8 is up here either as a 3-8 pair to make 11, or as the 8-2 down here to make 10. We also know in row 4 that we are still missing the 2, which has to be in one of these. And actually we can do more, because let's try putting the 2 in here. There is no 2 in these cells because we can never put a 2, 9 in here, and 2, 8 we've already established doesn't work because of the 8s here. So we definitely know that there's a 2 in here, taking the 2 out of here, and we get a naked single in row 4. So we get 2 and 8, and this helps taking out the 3 and the 8 up here. So we are left with a 4, 5, 6, 7 to make 11. And this 8 also finally gives us enough information about this cell, takes out the 8 here, and we can put in the 9. So now we can take out the 9s from here as well as here, placing the 9 as it's the only position left in box 1 to place the 9. Also now we get another 4 6, which kind of yes, goes around these boxes, but we do not yet know which way around they go. We still need to figure out the next step, which maybe we can find looking at column 5, where we have an 8 and a 7 down here, and we still need to put in, let's pencil mark everything, we need to put in 1 and 3, and then, yeah, maybe let's not pencil mark everything because that would be too cluttered. Let's do it smart way and only put in what we definitely know can work. We have 7 cage down here, which could be 1 6, but only one way, so it could be 6 and 1. It's here where we realize we can never put a 1 in here because we would need the 6 down here, which doesn't work. Then the 5 2 does not work because of the 2 here, but we could still put in 3 4 down here. So this should be the only options for the 7 cell cage, or the 7 cage total, and the 8 cage total could still be 1 and 7. It could not be 6 and 2, but it could be 5 3 in either direction, I think. So the next step is a little bit tricky to spot, that's why I remember it as well. So basically, maybe it screams deadly pattern already. If this was a 3-4 pair and this is a 3-4 pair as well, we would maybe, and I think definitely, have a problem later in the solve of disambiguating these. So if you really wanted to use uniqueness, you could, but we can also prove that 3-4 doesn't even work. If we place 3-4 in here, we get problems with this box. So we need to put in the options for this cage, which adds to 15 because it's between the 16 and the 14 cage. So this one adds to 15 with 1, 3, and 4 in here. So let's think about this for a second. We could have a 1 in here, which gives us 14. So we basically would be left with 8 and 6, which is, let's paddle back for a second. We can never put a 1 in here because we have a 1 already here, and we can place no 1s up here. So basically we can take out the 1 already, and these 2 options, we are left with a 3 or a 4. If we put the 3 in here, we still need 12 without using 5 7 or 3 9, so we can only use 4 and 8. Or if we put the 4 in here, we are left with 11 for these 2 cells, and we can't use 9 and 2, we can't use 7 and 4, so we can only use 8 and 3. So basically we can deduce from this that this cage is a 3-4-8 cage because there cannot be a 1 in here. I suppose we can pencil mark these 3 cells to make it clear. These should be 1, 2, 5, and 7, but we cannot have a 1 in here and the 5. So these 2 1s are the important factor. Now let's go back to the logic with these 3-4 pairs here. We want to find out why the 3-4 doesn't work, and let's assume we place the 3-4 in here. Then we get the 8 in this cell, and we get another 3-4 in here. And we also solve basically the rest of this column, because this cannot be a 3-5 now, so it would have to be a 1 and a 7. Now having a 1 and a 7 gives us a 3 in here and a 7 in here. Basically, important part is there's a 3 in this cell, and the 7 in here is also important because it rules out the 7 from these 3 cells and puts a 7 in here. Now we need to take a closer look at how these 4-6 cages interact, because that's the important part here, because it plays back into the logic down here. We know that these 2 cells have to add to 11 because of the 9, and we also know that this digit is the same as this digit, and it's the same as this digit. I'm gonna color these because obviously let's use these colors. We have these 2 are different, obviously, and these 2 are different, so we get that these 2 cells are the same, and obviously these 2 are different, so these 2 are the same. Now, having the 7 up here solves this 4-6 as a 4, which means we have a 4 here as well, and a 3-4 here, 3 and a 3-4 here does never work. So this is kind of yes, complicated way of disambiguating this box down here, but it's so far the fastest way of disproving that there could be a 3-4 down here. It's the only part of the solution path which I worry about being seen as a little bifurcaty, but feel free to message me if you find a faster way of disproving that this cannot be 3-4 down here. But that's what we found out. So if it wasn't clear, I'm gonna go over it real quick and put in the digits so you can see. If we have a 3-4 pair down here, so if we take out the 1 and the 6, then we have to put the 8 in here, take the 8 out, and we have to take the 3-5 out of here, put in 1, 7, and 3. But this 7 also puts the 7 up here, puts the 4 in here, here, and here, and the 3-4 breaks. So let's go back to the start and remove the coloring, and take out the 3-4 down here, and finally get our next 2 digits, which are a 1, a 6. Take out the 1 and the 7 here, but now we've also removed the 5-6 pair up here. We get the 4-7 pair, which gives us 3, gives us 7, and this 7 gives us the 5, and the 6, the 4, 6, the 4, and the 6. Let's see if we get more from this. Yes, we can take out the 5 from here and here. And I believe we can pencil mark, I guess, up here, which should be now 2, 5, and 6. Actually, we can take out the 2 pencil mark and put in the 2 in the cell, because we have a 5 and 6 pointing at the cell already. Now we have a 5-6 pair up here, and we also know that this cell right here has to be, I guess the same as this one, so we can put a 3-4 in here. But looking at row 3, we get 1, 2, 3, 4 is missing, and 7. We have a 7 pointing at these, so we get a 4 and a 7. Now let's not do it too quickly, and think about if we missed something. Yes, we did. We have the 4 placed in here, which disambiguates our 4 and the 7. These 7 takes out the 7 and the 3 from here. And do we get anything else? I'm not sure. So let's put in the pencil marks up here. Right here it should be easy. We have basically 6 digits given, so we are left with 3, 4, and 8 missing. There cannot be a 4 up here, so it's a 3-8 pair, and the 4 has to go in this cell, which solves, yes, the 3 in here, 3 in here, takes out the 3. From these cells we get the 1, we get the 8, we can take out the 8 from up here, and the 3 also gives us a 5 and a 3, and let's see, we have another pair left up here, which should be 2 and 6, if I'm not mistaken. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, exactly. We can not yet continue. Yes, we can. Basically, I've overlooked that earlier. We have the 9 right here, pointing at the 9 and 1 for ages, I think. I could have put that in. But the 1 solves the 5 and the 1. The 5 gives us the 5, 6, the 6 and the 2, and the 2 takes out the 2 and the 8 up here. Now we are almost done with the 2 4x4 squares we started with, so we are left with pairs everywhere down here, and yeah, quadruple still up here. The 3 and the 8 we still can't disambiguate, I think, so we need to shift our focus to the bottom left, where we are left with a 4, 8 in box 5, and the pencil marks down here would be 2, 4, 5, and 8, where the 8 can't be down here. Now the next step, which actually does involve the negative constraint, is when we look at column 3, or rather, yeah, maybe the step after it, so to speak, requires the negative constraint, but we first need to pencil mark these 3 cells, because we have a pointing to a 7 pair, so we are left with 3, 5, 6, and 8. We see that the 6 has to be in this top cell, and we push the 3, 5, and 8 in these 2 cells, but the important thing about this is that the 5 is pushed into these 2 cells. We can't have a 5 up here, so the 5 is in this cage and can never be in this cell, and this puts the 5 into this 2-cell cage. So basically this cage is now 5 and 2, which would be 7, 5 and 4, which would be 9, or 5 and 8, which would be 13. And right here we need the negative constraint to help us out, because we have 2 cages next to it that we know the sum of, and these are 7 or 8. And we know that if we put 5 and a 2 in here, we would have 7, which never works because it's next to the 8 cage. So we can take the 2 out of here and basically put it in here. And the next step is, assuming this was a 4 or 5 pair, we would have a sum of 9, which would also be next to the, or one higher than the 8 cage, so we would need a white dot, and there isn't one, so we can take out the 4 as well, and we are left with the 5, 8 pair, and can put in some more digits because this 5, 8 sees the 4, 8, so this has to be a 4, 8, and 4. And now we can use that we have locked the 5 into row 7 and row 8 in boxes 8 and 9, so it can never be in row 8 column 3. And we can take out the 5 and place the 5. And this does not help solving or disambiguating the rest down here, so we have to use the negative constraint again. And I wanted to do this earlier, but I'm going to do it now because I think it's prettier this way around. We can use the negative constraint actually on these two cells up here, because we can assume one arrangement and realize that it doesn't work. We have a sum of 12 already in this cage, and we have a sum of 16 already in here, so assuming we put a 3 and an 8 this way around, we would be left with a sum of 20 and with a sum of 19, which isn't possible because of the negative constraint. We would need a white dot in here, so we actually have to place them the other way around, which solves the pairs over here. So 3, 8 pair, and we know that this added up to 10, so we have a 7 and a 2, and we can take out the 7, 3 from here, and we can take out the 2 from here. So this 8 now is finally useful and disambiguates the 8 and the 5 and the 9, the 9 and the 7, and we are left with basically the bottom left of the grid to solve. And right here we can use some normal Sudoku to place not digits, but well, we can place digits actually, but to get some pencil marks. We know that the 9 is placeable right from the digits we already have, so the 9 is put in here. Then we know that down here we still need 3, 4, and 7, so we can put 3, 4, 7 in here, take out the 4 from this row. Right here we need a 1, 2, 3, and 4, so we can put in 1, 2, 3, and 4, take out the 4 again, and up here we are left with a 1 and a 2. So basically these are the only options for these 5 cells down here, and we quickly realize that we only have 2 options for this cage, and that is leaving out the 3 or leaving out the 4. We already sum to 15 right now. 15 with a 3 and the 7 would be 25, and with a 4 and the 7 would be 26. Now, remembering that this cage adds to 13, we can never make this cage add to 26 because it would need a black dot between these two cages, so we cannot put the 4 in here to make it a 4, 7, so it needs to be a 3, 7, and we finally disambiguate this 3, 4 pair down here, which actually gives us a 1, 2 pair and a 4. This 4 does not yet give us the final disambiguation, but it removes quite a bit of possibilities for this cage, which we need to look at next. We have only 2 options basically. We have a 1, 7 pair in here, and we have a 1, 2 pair in here. So we know that if we put a 1 in this cell, for example, we would be left with 1 in this cell and then 2 and 7 over here. Or the other possibility would be to have a 1 in here and the 1 in here, and then have the 7 here and the 2 down here. So basically there's always going to be a 1 in these two cells, or in these cage, these two cells, or in this cage. So basically this cage is either 1, 2, 4, which would be 7, or it's 1, 7, 4, which would be 12, and that does never work because putting in 12 clashes with a negative constraint again. We have an 11 cage up here, and putting a 12 cage next to it wouldn't work. So this cannot be the 7, so we basically get the arrangement of 1, 7 here and 2, 1 down here, and this finally solves the remaining digits of the Sudoku, and I'm actually quite happy that I only took about 1 hour to solve my own Sudoku. Yeah, it definitely had some tricky parts in it that I didn't remember quite so well, but I am glad that I found them, and hope that some of you stuck around, or maybe just watched the parts where you have struggled. Maybe watch if there was an easier way to do it. Let me know if there is an even easier way to do it than my own intended solution path. I'd be very interested in that. And please feel free to also tell me if you found a different way completely, even if it's more complicated. I'd be interested in that as well. If you managed to break into this puzzle in a different way, maybe use some famous theorems. Fistemophill is of no use here, but maybe Art's theorem can be used. I've seen people use it, and yeah, tell me what you think about this puzzle. But that should be it. I don't want to make this video too long. It's supposed to be a show of the intended solution path, and I think that's what I did. So thanks for watching if you did watch till the end, and yeah, I hope you enjoy this.